Hello. Today I will work through a set of questions with different difficulties that you may typically get in the examination on waves. Question 1. The solid line in the figure shows a transverse wave at a certain instant. After 0.1 second, the wave had traveled a distance of 3 cm, and it is indicated by the dashed curve. You are asked to find the wavelength and the frequency of the wave. This wave starts from here to here. Then the wave pattern repeats. Wavelength is the distance between these 2 points. We call it lambda. It covers 1, 2, 3, 4, 5, 6, 7, 8 divisions. Each division is 3 cm. So the wavelength is 3 cm times 8 equals to 24 cm. Then we need to find the frequency. In order to find the frequency, we need to calculate the wave speed first. The wave speed equal to the distance traveled by the waveform divided by the time taken. The wave pattern moved from here to here in 0.1 second. So the wave speed is calculated by 3 cm divided by 0.1 second. It is 30 cm per second. Then we can use the equation V equal to F times lambda. Frequency can be calculated by the speed over lambda. It means 30 cm per second divided by 24 cm. The frequency is 1.25 Hz. Question 2. The figure shows the shape of a transverse wave traveling along a string at a certain instant. Particle P here is moving downward. You're asked to describe the state and acceleration of the particle Q and R, and also state the phase relationship between P and R. Firstly, we have to determine which direction of the wave is moving. As P is moving downward, we can use a dot line to show the waveform a moment later, like this. You can see the wave is moving to the right. Now look closely at Q. It is at its lowest point and it changes direction from downward to upward. So Q is momentary at rest at that instant, and R is moving upward. Let's consider the acceleration of particles now. In a wave, the string will apply forces on the particles to pull them back to its equilibrium positions. As Q is at its lowest positions, force in the string pull Q back to its equilibrium positions. So Q accelerates to its equilibrium position with the greatest magnitude in upward direction. R is at its equilibrium position, so no force acting on R. The acceleration of R is 0. For phase relationship, we need to consider the path difference. The path difference between P and R is 1.5 lambda. So when P is moving down, R is moving up. So we say that P and R are 180 degrees out of phase. Or we can say that they are in anti-phase. Question 3. The figure shows a string fixed at both ends. The distance between the ends is 51 cm. Two identical sinusoidal waves travel along the string in opposite directions and form a stationary wave with an antinote at point P. The maximum displacement of particle P is 10 mm from the equilibrium position. What is the amplitude and wavelength of each traveling wave on the string? Firstly, let's recall how does a stationary wave formed. When a wave travels to the wall reflects the traveling wave in opposite direction. The incident wave and the reflected wave meet. They interfere and superimpose to form the stationary wave. At the position of node N, there is no oscillations, as the vibrations of the waves just cancel each other. At the position of antinode A, the vibration of the wave will add up to reinforce each other. So the stationary wave will look like this. At the antinode, the wave vibrates with the amplitude equal to the sum of the amplitude of the two traveling waves. Therefore, the amplitudes of each traveling wave will be 10 mm divided by 2. That is 5 mm. The wavelength of two waves is the same as the stationary wave. 51 cm is equal to 1.5 lambda. So the wavelength is 51 cm divided by 1.5 and equal to 34 cm. Question 4. The figure shows a displacement-distance graph of a transverse wave traveling along the x direction at time t equal to 0. At time t equal to 1.2 seconds, the particle P just passes the equilibrium position for a second time at that moment. You're asked to find the wave speed. Firstly, we need to find the wavelength. The wavelength is equal to the distance between the 3 cm and the 15 cm. So the wavelength is 15 cm minus 3 cm. That means 12 cm. Then we need to find the period. Now look at the particle P. As the question tells us that the particle P will go up, pass through the equilibrium positions, and then go up again, down to pass the equilibrium position the second time. So the time it used is 1.2 seconds and it used 0.75 period. So one period is 1.2 divided by 0.75. So the period will be equal to 1.6 seconds. Then we can calculate the speed by the distance divided by the time. The distance moved by the speed in one wavelength is 12 cm. The time it lit is one period, that means 1.6 seconds. So we can find that the speed is 7.5 cm per second. Question 5. One end of a piece of string is fixed to a wall. A wave pulse travels along the string at a speed of 1 meter per second towards the fixed end. Figure below shows the string at time t equal to 0 and time equal to 7 seconds. You are asked to draw the shape of the pulse at the time equal to 3.5 seconds. Now we look at the graph. Okay, this is the pulse. It will move to the right at the speed 1 meter per second. Now we consider this point. If t equals 0, the point is here. It will go forward by 1 meter when it is 1 second. and then go to the point P at 2 seconds. Go to the wall at 3 seconds. Then it will bounce back. Okay, so we look at the lower graph. The wave will bounce back. So at the 4th second, the wave should be go here. But be careful, okay? The wave enter, the first part enter is a trough like this. After the refractions, they will reverse. And then the crash will enter. And after refraction, there's only also a phase change. So the shape refract will be in a shape like this. And this pulse will continue to go to the 5th second, and then the 6th second, and here the 7th second. The question is that when it is at 3.5 seconds, only half of the shape go in. So when they refract, the top will become a crash. And the original crash is still outside the wall. So we have the crash here. These two parts of wave will add together. So the resultant pulse we can observe as 3 equal to 5 seconds will be like this. So I will erase the other part so you can see it more clearly. Okay, so a drawing. In question 5b, we need to sketch a graph of displacement time for the point P. On the string at a distance 1.0 meter from the wall during the period t equal to 0 to t equal to 4 seconds. The incoming pulse take 2 seconds, 1 second, 2 seconds to reach point P. So there's no vibration in the first 2 seconds. We can draw on the displacement time graph like this. Then from 2 seconds to 3 seconds, a trough, this one, will reach point P. So, and followed by a crash. We will have a trough and a crash. The pulse will pass at 3 seconds. From 3 seconds to 4 seconds, there's no displacement.